Every single Starlink satellite currently orbiting Earth has already executed collision avoidance maneuvers, and the scale of the problem those maneuvers are managing has grown so large that it is fundamentally changing how humanity thinks about the long-term survivability of the space environment above our planet. There are currently over 7,000 active Starlink satellites in low Earth orbit as of mid-2025. Every one of them is moving at approximately 27,000 kilometers per hour. At that velocity, a collision with even a centimeter-sized piece of debris releases energy comparable to a hand grenade detonating. A collision with a larger object, another satellite, a spent rocket stage, or a substantial debris fragment, would not just destroy the satellite. It would shatter both objects into thousands of new fragments, each one becoming a new collision hazard capable of destroying other satellites in a chain reaction that orbital mechanics researchers call Kessler syndrome. Kessler syndrome is not science fiction. It is a mathematically documented threshold beyond which the debris density in a particular orbital shell becomes self-sustaining. Collisions generating enough new debris to trigger further collisions faster than atmospheric drag can remove the fragments. At low Earth orbit altitudes between 500 and 600 kilometers, precisely where the majority of Starlink satellites operate, the time for debris to naturally re-enter the atmosphere ranges from years to decades. A major fragmentation event in this zone could render the entire altitude band effectively unusable for generations. To prevent contributing to this scenario, SpaceX has built autonomous collision avoidance directly into every Starlink satellite's onboard systems. The satellites receive conjunction data, close approach warnings generated by the United States Space Force's 18th Space Control Squadron, which tracks over 40,000 objects in Earth orbit and issues warnings when two tracked objects are predicted to pass within dangerous proximity. When a conjunction warning meets the threshold criteria, a Starlink satellite automatically calculates and executes an avoidance maneuver using its onboard krypton ion thrusters without requiring ground intervention. The volume of these maneuvers has been extraordinary and growing. SpaceX reported that in a 6-month period, Starlink satellites executed approximately 25,000 collision avoidance maneuvers. That number reflects both the scale of the constellation and the density of the debris environment it is operating within. As the constellation grows toward its authorized 12,000 satellite count and potentially beyond, the maneuver frequency will increase proportionally, demanding more onboard propellant, more computational resources, and more sophisticated autonomous decision-making from each satellite. The conjunction warning system itself is under strain. The 18th Space Control Squadron currently tracks objects down to approximately 10 centimeters in diameter using ground-based radar systems. But the estimated population of debris objects between 1 and 10 centimeters. Too small to track individually, but large enough to cause catastrophic damage at orbital velocities, is estimated at approximately 500,000 objects. These fragments are essentially invisible to current tracking infrastructure, meaning collision avoidance maneuvers can only address known threats. The 500,000 untracked centimeter-scale fragments represent a hazard that no current autonomous system can directly account for. SpaceX's response to this challenge involves several layers of mitigation beyond autonomous avoidance. Starlink satellites are designed with a planned operational lifespan of approximately 5 years, after which they are deorbited using their ion thrusters to ensure atmospheric re-entry within approximately 5 years of end of life, well within international debris mitigation guidelines recommending re-entry within 25 years. SpaceX has publicly reported a deorbit compliance rate exceeding 98% for satellites that have reached end of operational life. The design philosophy of building deorbit capability directly into every satellite from the beginning represents a meaningful commitment to responsible constellation management. But critics within the orbital sustainability community note that compliance rates and intentions do not eliminate the risk that a sudden propulsion failure across even a small percentage of a 7,000-plus satellite constellation could strand significant numbers of spacecraft in debris-generating orbits. The broader commercial satellite industry is watching Starlink's collision avoidance operations as both a model and a warning. Amazon's Kuiper constellation, which received FCC authorization for over 3,200 satellites, is beginning deployment. OneWeb operates hundreds of satellites in low Earth orbit. China's planned commercial constellations include authorizations for thousands of additional spacecraft. The cumulative conjunction interaction between all of these independently operated constellations, each running its own avoidance logic, each responding to the same conjunction warnings with potentially conflicting maneuver decisions, introduces coordination challenges that the current international space traffic management framework was not designed to handle at this scale. The United States government, through the Federal Communications Commission and the Department of Commerce, has been developing updated space traffic management frameworks. The FCC updated its orbital debris rules in 2022, reducing the post-mission deorbit requirement from 25 years to 5 years for low Earth orbit satellites, a change driven directly by the growth of large constellations. But regulatory frameworks operate on timescales measured in years, while the orbital environment is changing on timescales measured in months. The sky above Earth has never been busier. Every Starlink satellite dodging debris is simultaneously adding its own presence to the conjunction equation that every other satellite must navigate. The mathematics of coexistence in low Earth orbit are becoming genuinely complex at a speed that is testing the limits of every technical and governance system humanity has built to manage them. So here is the question that should make you think seriously about the infrastructure civilization now depends on. If a single major collision event in the Starlink orbital band triggered a debris cascade that rendered GPS, weather satellites, and communications infrastructure unusable for years, and the technology to prevent that scenario is still being developed, how much risk is acceptable in exchange for global internet connectivity? Follow this page right now if the hidden risks of the infrastructure orbiting above your head concern you as much as the benefits it delivers. Because this is one of the most consequential conversations happening in space policy right now, and we cover it with the depth it deserves every single week.